All right, so we are talking about the function of proteins. The first two proteins that we're looking at are binding proteins. The molecules bind to oxygen. One is myoglobin, one is hemoglobin. Okay? Myoglobin is different than hemoglobin. Myoglobin is found in the muscle. It is a store of oxygen until your muscle is absolutely in need of oxygen. Hemoglobin is a transport molecule that goes through the circulatory system and goes into the lung, picks up oxygen, and carries oxygen to the other parts of the body. Okay? Hemoglobin and myoglobin are different in that myoglobin is one single polypeptide chain. The hemoglobin is four that work together for good work. All right? Now, the hemoglobin made up of four subunits and pairs of two subunits. Alpha and beta are the adult versions. Now, what in the world is the difference between alpha and beta? Do you know? They have two different names. Not necessarily the way they, well, maybe a little bit in the way they're connected. It's this. They have basically the same amino acid sequence except for a few amino acids. So they're not identical. There are a couple amino acids that are different. All right? Now, those couple few changes in amino acid side chains actually changes how they behave. And when they work with the alpha subunits, you get a unique set of circumstances and behavior. Okay? The gamma, we're going to change the sequence, and again, just a few of the amino acids, and we're going to get a different version in the fetal hemoglobin. All right? Most of the time when we have different subunits, a lot of times they are just subtle changes off the base chain. Okay, but sometimes we have totally different subunits, totally different peptides. All right? So the alpha and beta fold the same, they look the same, they act basically the same, but they're different by a few amino acids. Okay? If I take, yes?
The chain in myoglobin, is that similar to one of the chains in hemoglobin?
Yes, they are very, very similar in homology, meaning that most of the sequencing is actually the same. Just small variations in amino acid sequences, okay, for many of the myoglobins and many of the hemoglobins. Although, here's what we do find. As we look through the variety of all different types of species that have myoglobin and hemoglobin, we can actually start to see diversity in their sequences. And so we can have very, very similar or very, very different amino acid sequences, but here's the deal. They all fold the same. There's myoglobin and there's the beta chain of hemoglobin. You can see, and you can actually count the 8 alpha helix in this better than you can in that animation about where they are. Now, here's where the similarities come in. Okay, this fold is called the globin fold. It's designed as an oxygen carrier, and here there are a few residues that are the same in every single hemoglobin or myoglobin. The positions of the histidines are the same because the histidines interact with that heme group, and it has to be covalently linked on one side, and it has to be close, but not so close as to make a bond on the other side. And that three-dimensional alignment is very important. So that is the same case through every one of them. The prolines tend to be the same. They end alpha helix. And so there are certain residues that are the same in every one of them. And then what we see are patterns of hydrophobicity and polarness in the fold or in the sequences. And so this is one we can scan for and estimate, is it going to be in this fold? All right, here is the binding curve of oxygen. And so we get saturation event between 0 and 1, 1 being 100% saturated, and 0.5 being, in a very important point, half saturated. Which has more affinity for oxygen? Great test question. Myoglobin? That sounds like a question, not an answer. Why?
Because it's more saturated under lower pressure.
Okay. Given any one of these pressures on this chart here, the saturation of myoglobin is higher than hemoglobin. And so let's say at 20, okay, torr and partial pressure of oxygen, hemoglobin not fully saturated, but myoglobin is almost 100% saturated. So the way you read this is at any pressure, you can see the difference. The one that has more bound has a higher affinity. Does that seem simple? Okay. All right, let's get some context. All right, have you ever heard of the unit torr? What is that with? Pressure of gases, right? Okay, let's think about this. What number did you remember with torr? 760 torr. Where? In the what? That's atmospheric pressure. All right, and so atmospheric pressure is 760 torr. Why do I not have 760 torr of oxygen? It's in a biological system, yes, but even in the lungs, when I breathe in, do I have 760 torr of oxygen? No, why? Air is made up of oxygen and what? Nitrogen. It is made up of 79% nitrogen, only 21% oxygen. So how many torr is that? Okay, check this out. 21% of oxygen. What is 10% of 760? 76. So I get 76 for 10%, 76 for another 10%, and 7.6 for 1%. So 6 plus 6 is 12, plus 7 is 19. Oh, wow. I'm doing magic, you know? I'm doing math without a calculator. Okay. The most you could ever get in terms of torr for oxygen is 160 in the lungs. Okay? Because there's only 21% oxygen in the atmosphere. And if you're at normal atmospheric pressure, you get 160 at the most. So this graph does not represent the atmosphere. This graph represents somewhere away from the lungs. Okay? What would happen to the saturation point if we were at the lungs, both myoglobin and hemoglobin? What would you predict based upon these graphs? In the lungs, what would be the saturation for both? What percent? 100%. Okay? You will never get that to happen because where's myoglobin located? In the muscle. Okay? Inside the muscle. The only time you'll ever see hemoglobin will be flowing through. Okay? And we don't actually get 160 even in the lungs because you have to have an exchange in the lung tissue, but we do get a high enough concentration of partial pressure of oxygen in the lungs to become 100% saturated. Okay? All right. And so we usually measure things by P50, half full, and so we can see half full for myoglobin is at 1 torr, and half full for hemoglobin is about 26 torr. Okay, you get about half full. All right. If you take a look at these are two different curves. One is sigmoidal and one is hyperbolic in terms of the dissociation. That's going to be very indicative of how proteins work, and so it's going to lead to tell us that hemoglobin is what's called cooperative. I'll talk about that word in just a moment. Hemoglobin is cooperative. Okay. The hemoglobin is the one that transports. Myoglobin only binds. All right. Now, hemoglobin's ability to bind oxygen is affected by several different things. Okay. Also, Hemoglobin and myoglobin bind to different things. Myoglobin can only bind to oxygen, okay? Let's say physiologically. The other thing it can bind to is carbon monoxide. That's not physiological, okay? In terms of transport, hemoglobin can bind to and carry protons, carbon dioxide, and oxygen, but oxygen is the only one that is bound at the heme. The CO2 and the protons are carried other places. Okay? Now, the fact that this word cooperative, okay, hemoglobin binds to oxygen cooperatively. Okay, what does this mean? The first oxygen to bind to hemoglobin of potentially 4 takes a lot of energy to bind. But the second one, okay, once the first one's formed, hemoglobin's affinity for oxygen actually increases. It's easier to bind. Once you have 2, the third one is even easier to bind. And by the time you have 3 of them, the fourth one's binding really, really tightly, really, really quickly. Okay? Because we have 4 subunits, we get increased ability for everyone that is bound. Myoglobin has only 1 affinity because it only binds once. Now you can see that by that hyperbolic curve. There is 1 rate by which the binding occurs. But hemoglobin, because it changes its rate or its affinity, depending upon how many things are bound, how many oxygens are bound, that's why we see the sigmoidal curve. So, myoglobin has a fixed affinity, hemoglobin has a changing affinity. And that's where that difference in the graph comes up. There's a difference between myoglobin and hemoglobin also in pH dependence. Okay, if you lower the pH or if it has a higher concentration of protons, you can say it either way, hemoglobin really doesn't like oxygen as much. It lowers its affinity for oxygen in the presence of acid. Myoglobin doesn't care. Hemoglobin, in the presence of CO2, it has a lower affinity for oxygen. Myoglobin doesn't care. And in the presence of a small molecule called BPG, 2,3-bisphosphoglycerate, if that molecule is there, oxygen is a lower affinity in hemoglobin, myoglobin doesn't care. It seems like everything tends to make hemoglobin less likely to bind to oxygen. Now, there are a couple reasons why. I'll talk about that in terms of pH and CO2. There is a fundamental reason why the presence of those 2 entities in the bloodstream would cause hemoglobin to release oxygen. Okay, there's a physiological connection there. Okay. Bohr was the first to observe this effect in terms of if it is more acidic, the affinity goes down. If it is less acidic, the affinity goes up for oxygen. And so you can see the Bohr effect. Now, why are these pHs important? Okay, what's normal? 7.4. Okay, and if you become a little acidic, 7.2, I actually release oxygen, and if I become basic, I actually hold on to my oxygen a little bit more. All right, let's think about this. When physiologically would you become acidic? Okay. When might you feel the burn? When you do what? When you exercise. You feel the burn. What's the burn? Does anybody know? Lactic acid. Now, lactic acid physiologically is this. You're breaking down glucose for energy in an anaerobic context without oxygen. Now, here you do. Here's what's the problem with that. You can only extract somewhere in the single-digit percentages of the energy of glucose without oxygen, and not 100% of the energy. So, if by chance the bloodstream becomes acidic, it's probably moving into muscle that is doing anaerobic exercise. If it's anaerobic, what is it lacking? Oxygen. And that's a signal for hemoglobin to release oxygen. Because it's a signal saying I don't have enough, this tends to allow hemoglobin to release more than it wanted to originally because we're underneath. Why would CO2 also signal that? When you break down glucose, what do you create? When you oxidize glucose completely, you create two byproducts. Okay? If I did this in general chemistry, I would say a hydrocarbon, if you add oxygen, what are the products? What? Water and CO2. And so if you're producing a lot of CO2, that means you're probably doing exercise. That means you are using oxygen. And so those are both indicators that exercise is going on and that you need oxygen to replace the metabolism reactions that are going on. BPG is an interesting little molecule. We didn't know about this until fairly recently. And in 1921, we had been studying hemoglobin for quite a while. If they actually purified hemoglobin absolutely pure, you remember, we go through all the columns, we do all the dialysis, and we get hemoglobin. We put it in the test tube. What happened was the hemoglobin, absolutely pure and only hemoglobin, bound oxygen just like myoglobin. The exact same parameters. This was not physiologically representative of what we found in the body. And so here, I isolated it completely, and it didn't behave the way that I expected it to. So any experiments with purified hemoglobin, absolutely pure, didn't reflect anything that happened in the body. All right? Took a long while. That's in 1921. Took till 1967 before we found this particular molecule in the bloodstream. It is BPG, we call it, and it's a molecule that is a regulatory molecule of hemoglobin. All right? It is not a glycotic intermediate, although it is derived from that. This is not a normal product of any metabolism. When you look at this molecule, what do you think about it? Characterize it for me. What should you see jumping out at you about this molecule? It's very electronegative. Very, very negative. Okay, it's small. All right, should be pretty soluble, but all of that negative charge there is important in how it works. All right, here is one version of hemoglobin. And so we twisted the hemoglobin around. There are 4 peptides there, and we've twisted them just a little bit. And what happens is, in the deoxy form, the form without oxygen, the little twists on every 4 of them create a hole the size of BPG. And so, in the deoxy form, BPG can fit inside of that hole and reduce oxygen's affinity for oxygen by about 26-fold. All right? Now, there's an important reason why that pocket is very good for BPG. Not only is it the size and the shape, but take a look at all the side chains. What are all the side chains of the protein? Positively charged. What is that little molecule? Negatively charged. How well do you think that thing fits in there? That's like a big old magnet stuck right in the middle of that. Okay? Now, that's great. It stabilizes the deoxy form of hemoglobin, meaning that it keeps it in that deoxy form. For it to pick up oxygen again, the first thing that it has to do is displace this molecule. Now, look at all that negative positive charge. That is stable. You need a lot of energy to kick it off. Okay? Now, this is great for one particular thing. If you're in the lungs, you pick up oxygen and you flow down to the big toe. At the big toe, the concentration of oxygen is so low that hemoglobin will start to release it. Okay? Now, as it releases it, What you don't want to have happen is as the hemoglobin continues to go on, you don't want hemoglobin to pick up oxygen from the little toe and bring it to the lungs. That would defeat the purpose. So when it releases, it creates this little hole, BPG gets inside, and it locks it so that it cannot pick up oxygen until there's an overwhelming energy source or a large gradient. There's no gradient in the body, no large enough source of oxygen to displace it until you get where? The lungs. The high concentration of oxygen provides enough energy to kick out the BPG. That's the only time it'll pick it up. And so once hemoglobin, this is the transport, once it lets go in the body away from the lungs, it will never pick up oxygen until it comes back up to the lungs. This allows us to efficiently deliver oxygen and not take it away from places that it needs, just randomly. Now, how does fetal hemoglobin get its its oxygen from the maternal cells, the red blood cells? What happens is, in the fetal gamma subunits, okay, they're a little bit different than the beta subunits. Most of the positive charges in the BPG pocket come from the beta strand. If I switch it with the gamma strands, it has less positive charge. BPG fits in less tightly. So if BPG fits in less tightly, then consequently, hemoglobin binds to oxygen easier. And so fetal hemoglobin will always have a slightly higher affinity and be able to take the oxygen from the adult hemoglobin because it binds to BPG less. Okay? Now, once you get past the stage of being a fetus and you're in operationally or breathing in the air, there is a developmental stage where you stop creating the gamma side chain or the gamma chains and you make the beta chains to become the adult version. Yes?
So after it picks up the oxygen from the mom, how does the fetus release, how does the hemoglobin release the oxygen if BPG doesn't fit into it as well?
Right. The fetus has a lower concentration of oxygen all over its body. And so it will pick it up from the mother and then it will release, but the lower overall, because hemoglobin has a lower affinity for oxygen, a higher affinity for oxygen, it doesn't deliver as well. And so we're balancing. This is the only source where I can get the oxygen, so it has to have a higher affinity to grab it from the mother's blood, but it delivers a lower amount throughout the body. And so in terms of mass per volume ratio, the fetus may have a larger volume and can deliver more, even though it's delivering less each cycle. Because of the volume mass ratio, it delivers enough that the fetus needs. Okay, binds less strongly, we talked about that, and it's just a small substitution of a few of the positively charged amino acids. All right, what we're really talking about in terms of being cooperative is another word called allosteric. There are allosteric interactions that are happening between the alpha and the beta subunits, okay, that cause these differential functions. Now, we know this because of this. If we isolate alpha subunits alone and put them in a test tube, the alpha subunits will float around as individual proteins, look and behave just like myoglobin. Okay? We can take a collection of just beta subunits, put them in a test tube, they will form a tetramer. So 4 of them get together. But they also behave just like myoglobin. There's not an interaction between the two that changes their affinity the same way as the alpha and the beta coming together and working together. That means somewhere in the amino acid sequence between the alpha and the beta, there is some sort of interactions that are causing them to talk to each other or change their behavior as things move. And so these, the tetramer that is alpha and beta is allosteric. All right? In terms of the allosteric interactions, mainly it is the kind of interactions you can make between the two alpha and beta subunits. And really, it's a lot of salt bridges. Okay? In the oxygenated version, the C termini, okay, so that last amino acid, the negative charge is in the solution and moving around. It's really loose. Okay? But when it gets into the deoxy form, what happens is the C terminus gets close to a positive charge. And so the C terminal negative and this positive charge locks together, and in the deoxy form, there's less movement. Okay? There's more stability in the fold and less movement. So what we actually talk about is the quaternary structure, the structure between the four subunits. If it is deoxy, it is called the tense form because it is locked. It has a lower affinity for oxygen. The tense form is also enhanced by the BPG getting in there. The oxy form is termed R, relaxed. It has freedom of movement and it has a higher affinity for oxygen. BPG is moved out and the C terminus are able to move around. Okay, so the tensed, less affinity, relaxed, more affinity, was developed for hemoglobin. From now on, there is the tense formed and the relaxed formed of lots of binding proteins. It has nothing to do with if that particular protein is tense or relaxed, like it is for for hemoglobin. It just tense is less affinity for the binding ligand, relaxed is more affinity. So this is a generalization now we'll use for all proteins that bind, tense and relaxed. Not only are the salt bridges created at the C termini, there are other salt bridges that are formed in the tense form all along the between the two alpha and beta subunits. All right. Now, these salt bridges are very far away from the heme, where oxygen is actually bound. But these bonds that are very far away affect the heme and its ability to bind to oxygen because the heme is connected to histidine, the histidine is connected to the F helix, and the F helix is connected to everything around. And so if you have to move that iron on the heme, you've got to twist the entire protein just a little bit. And to twist them, you would have to break those salt bridges. And you would have to break the salt bridges of the BPG. And so it doesn't take a lot of movement to cause that thing to pop out or to break those bridges. But it does cause a lot of energy to do that transition. Okay? And it's a small movement. We're talking 3 or 4 angstroms worth of movement. That is not a lot of movement. It's about as much movement as I can get my daughter out of bed in the morning trying to get her to school. Yeah, she's 16. Oh my gosh, it's a battle trying to get her up. All right, but it's all because it's covalently linked. Okay, and it drags and it has to move the rest of the chain. Okay, the binding of the fourth oxygen is 300 times faster than the first. Okay, why in the world is that? Okay, why would that last one be so much easier than the first? Okay, if I'm in the tensed form, I've got all these salt bridges, right? I got BBG stuck up in there. What has to happen for oxygen to bind? Oh, you got to break all these things, right? The first thing that you have to do is twist it around and really break that binding pocket for BPG. The first bonding is the most energetic because it's got to pop out BPG. All right? That takes a lot of energy. The second one, when it binds, will break a few of the salt bridges, but not that big BPG, so it's easier. The third one has to break a few more. By the time you get to the fourth one, the whole structure is in the relaxed state. So it really doesn't have to break anything. And so it is much more able to bind. Okay. And so, I just said all of that right here. Okay, All right. The reverse is true. As soon as you release the first, some bridges start to form, which causes the second one to fall off faster, which causes the third one to fall off faster, which causes the fourth one to fall off faster. And so it will be cooperative. It'll go in both directions. I will start picking up very quickly, and I will release very quickly everything. You don't find a hemoglobin floating around with two. It's either kind of an on-off situation where it releases completely or it fills up completely. Now, to determine if a protein is allosteric and cooperative, okay? Allosteric and cooperative, you have to have more than one subunit. That's a given. Because the cooperativity and the allosteric is between at least two subunits. You can plot this. You can plot the concentration of whatever you're looking at in one axis, and then the saturation divided by 1 minus the saturation, and you take the log. And if the graph does this is called the hill plot. If the graph becomes 1, it is not cooperative at all. If the graph is greater than 1, then the number of the slope actually approaches the number of subunits that are there. And so for hemoglobin, it has 4 subunits. The hill plot says that 2.8 of them are important to helping the next one. So by the time you have a third, there's my daughter getting up. By the time you have a third one bound, then there's no more effort. There's nothing else to break. All of the available help has been given by that time. And so the hemoglobin has a hill plot of 2.8. It shows about 3 of them contribute positively to the binding or will contribute positively to releasing, depending on which direction you go. Now, I did say that hemoglobin transports other things than oxygen. Actually, you really don't transport carbon monoxide. It's bound so tightly it doesn't actually release anytime. So that's not really transporting, it's just holding on to it. Oxygen, it does. It picks up and releases under physiological conditions, so that's a transport. CO2 is transported. Okay. Most of the CO2 that's produced in the body, because as we break down proteins, carbohydrates, and fats, we make CO2. Most of it's transported as bicarbonate in the bloodstream. It's actually the buffering system of the blood system. And so it goes around as bicarbonate, and when it gets to the lungs, the bicarbonate can be converted to CO2 and it can leave. Some of the CO2 can actually be carried by hemoglobin, not at the heme. Okay? The molecular geometry doesn't allow the CO2 to get up into that space. What happens is the N-termini of the, I believe it's the, I can't remember if it's the alpha or the beta. It's one of those. I'll look that up. But the N-termini actually reacts with the bicarbonate, and it creates a carbamate. Now, what is the N-terminus supposed to be charged all the time, every time? Positive. But if I react it with this CO2, I make it negatively charged. This, in the deoxy form, usually you have a positive charge next to a positive charge. It helps make things become relaxed because they are repelling each other. But once you put on a CO2 on that and create it negative, this positive charge doesn't repel, it attracts. It actually helps stabilize the tense form. But you get two CO2s reacted to the intermini, and they will float on the intermini until you get to the lungs, in which everything gets broken up in terms of all of the salt bridges. Those intermini become a little bit loose, and the reaction reverses and allows the CO2 to leave. And so it can carry one oxygen in, for each of the chains. So 4 oxygens in with the hemoglobin, it can carry 2 CO2s back out to the lungs. But it does it by reacting it with the intermini. Okay. And it creates another salt bridge. Now, one other thing that hemoglobin can actually bind to is protons. Protons are bound within the amino acids of the hemoglobin within the histidine residues. Not the 2 that are around the histidine, not around the heme, but other histidines that are within the protein itself can bind to the protons, carry them into the lungs, and in the reaction to create CO2 with bicarbonate, you need a proton, and so that is afforded and allowed to react to create CO2. And it is most likely I already answered, histidines, because they have the pKa that is very close to the pKa of the blood. All right. So, in terms of hemoglobin, its affinity for oxygen is changed by 4 different things: oxygen, CO2, BPG, and protons. Okay? 3 of them are negative. 1 of them is positive. You should understand which ones are the negatives and which ones are the positives. Okay? Oxygen is a positive, CO2, BPG, and protons are the negative. Another way to talk about protons or the acidity is you can call it the Bohr effect. And so they may not tell you it's a pH, but they may say the Bohr effect, and that is directly related to pH. So what happens is this protein has a different dissociation constant, a different affinity for oxygen based upon the environment it is in. And so if it goes in the bloodstream from different environments, the entire protein changes its affinity every time it hits a different environment. And so they are, it is an allosteric protein, which means it does not have a fixed property. The property of that particular molecule changes depending upon the environmental conditions in which it is found. All right. That is its normal working. Hemoglobin normally transporting oxygen, CO2, and protons into the lung and back and forth. One disease that we found with hemoglobin is called sickle cell anemia. It's predominant in the African American population, 4 per 1,000 in the U.S. It is fatal due to infections, renal failure, cardiac failure, and thrombosis. Okay, and so sickle cell, not necessarily something that is wonderful. You can actually see the effects. You can see 2 red blood cells. One, the one we want to see, and one that is the sickle cell. Okay, why is it sickle celled? Because it looks like a sickle. Okay, and so red blood cells are supposed to be nice, round, kind of flat. That nice, round, kind of flat easily goes through little capillaries. And it bounces through and gets taken through and goes through with no problem. But that long, sickled thing gets into a little capillary. If it is in one direction, can flow really good, right? What happens if it twists? Not good. What happens? It gets stuck. Okay, so what if you get stuck in the blood vessel? That means no blood flow on that other side. There's no blood flow on the other side of that dam. What happens to that tissue there? It lacks what? Oxygen. And without oxygen, we die. Not good. Okay? So why do we get a physiological change to look like the one in the front versus the normal. Okay? It is all because of hemoglobin and one single change in the amino acid sequence. Okay? One change. On the outside of the cell, you should have residues, polar residues, because that's interacting with water. We take a glutamic acid, which is a negatively charged amino acid that should be on the outside interacting with water, helps make the hemoglobin soluble, and we change it from glutamate to valine. Valine is hydrophobic and now sticking on the outside. Hemoglobin inside the red blood cell likes to behave as the 4 proteins in a unit, but they float around by itself, those 4 by itself, and it functions. With that valine there are certain conditions in which this bundle of hemoglobin binds to another hemoglobin, which binds to another hemoglobin, which binds to another hemoglobin, which continues to bind hemoglobins like Legos, and it puts every single hemoglobin in that red blood cell in this big, long tube. Okay, the cell's only this big, and if that tube gets bigger and bigger and bigger and bigger and bigger and bigger and bigger, it distorts that round red blood cell into the sickled blood cell that we see. Okay. Now, not only is it bad that it might block the blood vessels, okay, that's thrombosis. Okay. It also said there was renal failure. What is renal failure? Kidney. Okay, why in the world would this affect kidneys? 2 reasons. Give me one of 2. Oh, no guessers. Okay. It's the filtering place, right? To filter it, it has got to get down into very, very small vessels. So the sickle sticks up and blocks those out. So that's one issue. The second issue, your blood is always sickling. So the kidney detects it as needing to be getting rid of. So your kidney is working overtime all the time, getting rid of sickled blood cells when it shouldn't be. So it's working too hard. And so we can have renal failure from that. So those are 2. Thrombosis and renal failure were 2 of the things that we talked about initially as being an issue. And so we'll talk about the rest of this a very long time from now. And you will have forgotten everything that we've talked up to this point in time. All right?